Hello and welcome once again to the continuation of atomic structure for class 11. I am Sudhanshu Tripathi welcoming you to continue with my extensive program on atomic structure aiming at NEET and IIT JEE, or the reverse way, IIT JEE and NEET. Basically, my programs are meant for IIT JEE, but since preparation for NEET is a subset of that, say, universal set, as you guys have learned set theory in your lower level school. So the only problem with the NEET aspirants is to be ready to learn more things than what possibly will be required for NEET. But since you are interested to have a good position in all India level in the NEET, it is always better to have a preparation like IIT JEE Advanced. Now, last time we had a discussion on electronic configuration up to 30, but this is not required for you. I mean, those of you who are attending my Zoom direct live program. But since it is a program for the public, anybody can watch. So I am once again drawing the outbows order. Uh, which orbital will be filled first, then which orbital, to know that the above order, which is based on Madelung's rule, as you also draw, make a practice. Again, there is no harm in making practice again. And then you have to draw slanting lines. Now I'll change the color. Overlapping with these orbitals. Of course, you can have 8s, 8p to show that then the next one comes to 8s. So first 1s2, 2s2, 2p6, 3s2, 3p6. Then comes, you have to follow the arrow mark, 4s2, then 3d10, 4p6, 5s2. Then after 5s, after every p comes the s of the higher cell. That starts from 3p. Starts from 3p. Then after the S comes D. That is for only fifth cell, but not for the sixth cell. 4D10, 5P6, 6S2. But see, we had left out 4F, whose energy level will come later than 6S, then 14, then 10, 6, 2. Then the same trend will continue, 14, 10, 6, and then the new that is ready to be filled, not by us, but by those who will prepare synthetically the 119th element, which they are struggling very hard to prepare. Now, we should go to the anomalies. The anomalies in 3D series, as you already know that in the transition block, the d block, where the d electrons are filled, the d orbitals are successively filled, or you may say its number increases. So nobody is filling, its number increases. So that uh, the next electron, you find it is filling, it is appearing in the increment of 3D or 4D or 5D. These new electron which is being added in the configuration is called the differentiating electron. A differentiating electron means electron which differentiates that element from its preceding element. So the successive electrons are called differentiating electrons. So they go to the D subcell. That is why the middle portion, as you know, is called the D block, which are the transition elements. And the first transition element is called the 3D series, where 3D1, 3D2, 3D. So I think it's now necessary for me to bring you the periodic table, because that will uh, once for all we will settle the matter. While we study periodic classification, then this will be already in our mind. So I asked you not to write the configuration of 24 and 30 because they have anomalous, this chromium. This is 1s2, 2s2, 2p6, 3s2, 3p6. What we will do from now, this becomes the configuration of argon. So the way to save time is to write argon configuration. That means you have gone up to 3p6. There is no need to write every time 1s2, 2s2, 2p6, 3s2. It is understood. Then after argon configuration, it comes, you know, it should have been 4s2, 3d4. But here there is an anomaly. One electron will come. This is wrong. The correct one, because they are so close in energy. So the half filled and fulfilled D subcell stability. Because in the +2 level, you might get a subjective question as to why such an anomaly happens. It is due to the half-filled and fulfilled D subcell stability. Now see, when it is in one way, oh sorry, one electron short of half-filled or fulfilled. Two electrons coming from 4s to 3d is not possible. It's possible, you'll see it is possible, but it's very, very rare. But one electron can exchange. So when it is 1, so it's 4, but actually it becomes 5 and this becomes 1. So this is the correct configuration. And if you draw the box diagram, you'll find large number of unpaired electrons. Hund, 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 and here also hund. Poly will never come. So in chromium, there are 6 unpaired electrons. So for transition metal, we will not write a lone pairs. In fact, there is no lone pair here. 4s has become 1. But we will not write lone pair. Lone pairs are written for normal elements, not transition elements. Okay. So that is due to the the uh, symmetry energy and pairing exchange energy. How you will get 2 marks energy of a half-filled uh, d subcell. Now, these d orbitals which are degenerate having same energy, the electrons get exchanged. This can come here, this can come here. So there will be 4 exchanges for the first electron, 3 exchanges. 1 to 2 is same as 2 to 1, will not count. 3 exchanges for the second electron, and 2 exchanges for the third electron, and 1 exchange for the fourth electron. So total number of exchanges will be 10. 4 plus 3 plus 2 plus 1. So the number of exchanges is more. If it is D4 and 4s2, then the number of exchanges will be less. So more the number of exchanges between the d electrons, more is the energy released. That is called the exchange energy. And moreover, there is another energy which is called symmetry. If the orbitals are filled symmetrically, all are half filled. So from a distance, you look like every orbital is having single occupancy, and the entire assembly will be looking symmetrical. That will give stability by producing some energy called symmetry energy. So because of that, the half field stability, and I will tell you the full field stability, exchange is not there because they are all paired, but symmetry energy is very high. All the D will be doubly occupied, paired, so the symmetry energy is high. This is for uh, D5 chromium, and only symmetry energy for copper, D10. I'll just ask you to write copper, which is 29, argon configuration, 3D. It should have been 3D9 for S2, 29, 3D9, but it is, I'm sorry, but it is one sort of becoming fulfilled. So one electron will come. So the actual configuration which you will write, no more you will write this, no more henceforth you will write 3D10 4s1. So this is the correct configuration, and here there is only one unpaired electron, and that is in the 4s orbital. So this is the full field stability because of the symmetry energy that is uh, produced for rendering a high stability for this configuration, full field stability of DS subcells. So after we have finished up to krypton, then we will go for you will write at home the configuration of all. You can easily write, I don't, but for now, can you write down the configuration of say you have gone up to 36, so bromine you have written. I want you to write, say, platinum. No, 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 not platinum. To write, say, tungsten, the atomic number. If you apply the magic number, you can get 74. We'll be revising that in periodic classification. So you just see what noble gas is coming before that. It is always better. You see, this is what I'm asking. You write xenon configuration. You are entering into the 6th period. Then any new period begins with the S subcell. The number is the principal quantum number is the period number. That means 6. And you just proceed, walk over the elements. There are two in the S block, 6s2. Then you are entering into the D block. Before 6s, I mean before D, 6, after 6s comes what? C to the,
Sir,
yes, Bismarck?
after S block,
No, no, no. After 6s comes what? In the Madelong's rule, in the Aufbau's order, you see.
is, sir, 4F.
6s, then 4f. 4f means you are entering into here. This is 4f series. This is 5f series. This is called lanthanides. This is called actinides. Short notation of lanthanides or lanthanoids or lanthanones is Ln. And actinides or actinones or nodes. This is An. So since it is here, that means you have already crossed the 4F series. 6s2, because you see there is a transition 57 to 72. That means you have definitely crossed the lanthanide series. So you just count there are 14 here in the bottom. Although lanthanides include lanthanum, the mother and the children. I'm just kidding. 15 elements. That is the new concept. Previously, they were saying 14 lanthanide elements. Lanthanum was not included. Now, lanthanum is included in the lanthanide series. Anyway, so since you are jumping from 57 to 72, undoubtedly you will take 4f14. All the 14 electrons are filled up. So then you count 5D, to what extent you go count 1, 2, 3, 4. So you write here, it is Genon configuration. Just don't write 1s2, 2s2, 2p6, 3s2, then 3d10, 4s2, because already you have filled up. Start using that trick. Unless you use the trick, you might make mistakes. 4s2, then 3d10, then 4p6, then 5s2, then 4d10, then comes 5p6, then comes 6s2, then 4f4, 6, and then 5p6 is xenon. Fifth period ends with xenon. Then that is understood. After xenon 5p6, 6s2, then 4f14, xenon configuration, you know, write 6s2 way ahead because actually it has got the highest energy. Because I'll tell you just after a bit about screening effect. Then 4f14, then we count 5d. How many? How many?
4.
Sir, 4.
So you have to open definitely the actual valence shell, no doubt about it, but also open the one which is having unpaired electrons, the n-1d. And sometimes in the lanthanide series itself, you have to also open 4f, where you find unpaired electrons staying there in 4f. So it's not necessarily it's full. It's full, but 5d is not full. So wound. So there are four unpaired electrons and one lone pair. You might be thinking of asking a question because here you also find the D is one sort of half filled. Why not then one electron will come here like chromium to make it 5d5 6s1? Doesn't happen. The simple answer I wrote symmetry energy and the exchange energy is for getting a full mark in your board examination if at all you get a question. Why this anomaly? But the reality lies in quantum mechanics, the calculation quantum mechanics. So the such anomaly is not found in tungsten. It is found in chromium, and below chromium is molybdenum, yes. And when we start the 5D series, which in which tungsten comes, there will be very, very less anomalies because of some quantum mechanical effect, which I will tell you later in a uh, very, very general way. What we just I sound you, s- a very interesting effect comes into force while you enter into sixth period elements, seventh period elements. That is called relativistic effect. The quantum mechanical relativistic effects comes into force, which makes so many, changes in the physical properties, electronic configuration, others. That is why we will know where are the exceptions. Here, you don't find any exception. I'll tell you where you will encounter or meet exceptional cases or anomalous. Here, there is no anomaly at all. Now, I can ask you to write down, uh, say, same bismuth 83. You'll see to the periodic table if it is given to you, or continue if you do not have a periodic table, you do not know bismuth belongs to the sixth period. It is a continuation of the same tungsten ending with mercury and then thallium, lead, then bismuth. If you don't remember that, then you cannot remember the noble gas coming before it. But once you remember xenon is coming, so xenon, start with xenon configuration. See, otherwise, if you do not remember where is the position of bismuth in the periodic table, then you count the up to 83 and follow the Madelung's rule. No harm about it. So this will be 6s2, 4f14, 5d10. You have already traversed, walked over these entire 10 elements. Then you count 6p, 1, 2, 3, just counting. If you have periodic table in front of you, then you can count. Then 4f14, 5d10. Then you have to come here, 6p. Don't write here because 6p has a higher energy than 6s. That is the penetration effect that we already know. But why there is a topsy-turvy, why there is a reversal, that, we will just now know. This will be 6p3. And since 6 is open, so 6 is the valence shell, and there are 3p orbitals. This is a pair. This is so one lone pair and unpaired electron 3. So in all the groups, you find the electronic configurations are similar. Same number of electrons in valence shell, although the principal quantum number increases one by one as you go down one by one down the group, but the electronic configuration are sometimes identical, but in some cases, like in group 6, as you find, it is little different. Supposing group 6 chromium, molybdenum, they have 6 unpaired electron. This is 4s1 3d5, this is 5s1 3d 4d5, but here there is no anomaly. This is 6s2 and 5d4. So there are 4 unpaired electrons. Seaborgium, I'll tell you later, because their electronic configurations have not been determined. So we can just speculate the same trend will be followed without any anomaly, because these are so unstable and so short-lived that it's not possible to find the chemical properties. If you find the chemical properties, then only you will be ensuring what is its valency, how much electrons it can use to form bonds. Then you will confirm its electronic configuration. Just you can speculate without any anomaly here. So, so why? Before anything, let me tell you about the screening or shielding effect, which we'll be doing in a very big scale in periodic classification. We'll be using the Slater's theory to determine the screening constant, the mathematical calculation involving the screening, how much screening it is making so that the effective nuclear charge is being different from the nuclear charge. That calculation will be doing later. The shielding effect. The inner electrons act as a mechanical barrier, or screen or shield to reduce the nuclear pull. This is called screening effect. Just like you are sitting in front of me and nobody is between you and me. So I can see you, interact with you, attract you uh, more. But if some others, they come in between in lower cells, inner cells, then they will act as if they are screening, they are shielding. This is a mechanical barrier obstructing the nucleus to see clearly the valence electron, because it is the valence electron which is responsible for all chemical properties. So the valence electrons, get less nuclear pull because of the screening effect. And more the screening effect, less the nuclear pull and more the energy of that electron. Less the nuclear pull, more is the attraction, more is the electron being attracted towards the nucleus, and less is its energy. So, you must write down here more screening effect. How much screening effect we won't calculate now. Or screening effect is uh, is inversely proportional to the nuclear pool. More the screening effect, then less the nuclear pool, and less the nuclear pool, more is its energy. So directly proportional to energy of the valence electron of who is suffering from the screening effect. It is the valence electron which is suffering from the screening effect. These guys are obstructing and not able to interact properly with the nucleus. So if the screening effect is more, then the energy of the electron is more, because nuclear pool is less. It will go further, away from the nucleus, and hence it will have greater energy. The more it comes closer to the nucleus, attraction is more, less is its energy. Energy of valence electron. Got it? Is it going fine, Miss? I'm sorry, Mr. Mahanti and Mr. Tripathi.
Yes,
Yes,
sir.
sir.
Mr. Mahanti,
Yes, sir.
good. So, what happens? Why? Supposing we have not filled for 3D. Before filling, 4S is less than 3D. Only penetration works. Relative penetration of the orbitals. But after filling, which is the case, nobody is really filling. After filling, 4S is greater than 3D because screening effect sets in. I am telling you, because 3D is really a inner electron. 4S is the real valence electron. That's why I say really 4S, NS is the valence electron. N minus 1D is not really. I'm sorry, theoretically. But since their energy value difference is very small, they also jump into action for showing oxidation state or forming compounds with participation of d electrons. So once it is filled, which is reality, then 4s, because of the screening effect of 3d electrons. Same thing happens with other transition series. 3D electrons now screens additionally to the 4s electron, so that more is the screening, more is the energy, and hence 4s will acquire higher energy. Therefore, during ionization, 4s goes fast. Ns electron goes fast, and then n minus 1d. Because the one which is more energetic is more unstable. So when you apply energy to knock out electron, first it will go from Ns because it has got higher energy. Had you following the Madelong's rule as supreme, then you will remove first from n minus 1d, because first 4s2, then you write 3d4 or some 3d7, then you electron. Supposing I'm giving you an example. Supposing I'll say write down the configuration of Fe2 plus and Fe3 plus. So configuration EC in the ground state. Now first you write down iron. First you write down the neutral atom iron. This is argon configuration 4s2 3d6. Then you have to remove two electrons. Then Fe2 plus, tell me what will be the configuration, Swayam?
Sir, argon 3d4 4s2.
Bisma?
Sir, argon 3d6.
Precisely, ମୁଁ ଏତେ କଥା କହିଲା ପରେ I'm refraining myself from talking in Odia, only for your good. You could not understand, Mr. Mahanti, that because 4s has higher energy than 3d, when electron will be lost, it will be lost from a more energetic orbital, which is more unstable. Then successive electron, after exhausting all electrons from the ns, 4s, 5s, then n minus 1 d's turn will come. Sethipai, this will be, I'll write 4s0. Just for fun, just for style, I'll show you that it is 4s0. You may not write, but I used to write 4s0. And the number of unpaired electrons remain the same because it was paired. So whatever unpaired electrons were there in the neutral iron atom, same will be the case in ferrous ion. Do you understand, Swayam?
Yes, sir.
So why did you commit a mistake? କାହିଁକି ଭୁଲ କଲ ଏମିତି? 3d4 କାହିଁ କରିଦେଲ? ତମେ
Sir,
ସେ
ଭୁଲରେ ହେଇଗଲା।
ତମେ କ'ଣ ସେଇ ଅଭ୍ୟାସ କରିଛ କି? ଆଗ 4s2 ତାପରେ 3d ଲେଖୁଛ?
ନାଇଁ sir, sir ଆଗେ 3d ଲେଖିଛି sir ଖାତାରେ।
ମୁଁ କାହିଁକି ଆଗରୁ ପ୍ରାକ୍ଟିସ କରିବାକୁ କହିଥିଲି ଏଭଳିଆ? ବିକଜ ଆୟନାଇଜେସନ କଲାବେଳେ ପିଲାମାନେ ଭୁଲ କରିଦିଅନ୍ତି। ଯଦି 3d ଟା ପଛରେ ଲେଖିଥାନ୍ତି 3d ରୁ ଇଲେକ୍ଟ୍ରନ ନେଇଯାଆନ୍ତି। No, it's wrong. And Fe3 plus କ'ଣ ହବ? It will be having 24 electrons and this will be having 23 electrons. So argon, then
3d5.
3d5, and finally I write 4s0. So the number of unpaired electrons get changed. It will be 5 instead of uh, uh, oh, I'm so sorry. It was 6. The unpaired electron is 4. देखो कहीं किसी को no. This is being a public video. You are supposed to find my mistake. If I make a slip of my pen or tongue, then you have to immediately point out, because this is being recorded once for all. So hund, then folly. There are 6 electrons. The number of unpaired electrons is 4 in both iron and ferrous ion. Got it? Not 5, 4. Are you?
Yes.
Then why did you not point out? In both the case, unpaired electron is 4. But in ferric ion, the number of unpaired electron is 5. Because one electron has been knocked out from the 3d after finishing, exhausting the 2 electrons from 4s. You got it?
Yes, sir.
Yes, sir.
Then we'll see the anomalies in the 4d series. In 4D series, you find lot of anomalies. which cannot be explained by half-filled, full-filled stability theory. Now see, all quantum mechanical calculations are needed, which is not in your in your code, so we have to leave it. Only learning that anomaly starts from niobium, molybdenum as usual half-filled stability, technetium no, ruthenium. So here are the anomalous. And palladium suffers from a great anomaly. And as usual, copper fulfilled, silver is fulfilled. So let us write down niobium. If you do not remember, then you look to the periodic table 41, then add 111. So niobium and its previous noble gas is krypton 36. Then you are entering into the fifth period. You look to the fifth period here, where niobium comes in the fifth period, the 5s2. Then you have to count 4D. You just write down whatever will be according to Madelung's rule. This is 5s2, then 4D. How much? हिसाब करूँ एटी 36 तुम पाखे तो पिरियडिक टेबल ना तेणु 36 ये भाव 36 पर 8 दीटा
3.
38
3.
33 किंतु एटा wrong. There is one electron because the energy difference is so small that in some cases anomalies occur even without the half-filled full-filled stability considerations, because that has been verified quantum mechanically by doing a calculation which is done in higher level, that yes, the 4D4 configuration, 4D4 5s1 configuration is more stable, less energetic than 4D3 5s2 for niobium, particularly niobium. So this will be wrong. So this will be 4D4 5s1. And here you find there are 5 unpaired electrons, which have been corroborated by the dipole moment experimental study. 5s1 4d4 instead of this is the correct one. One electron exchange happens. Then molybdenum as usual, +2 student can explain through half-filled stability 42. This will be krypton configuration 4d5, 5s2 4d5, sorry 5s1 4d5. So there are 6 unpaired electrons like chromium, so there is nothing.
Yes,
Huh?
sir. Sir, जो नायोबियम रे लिखले सर 5 तापरे गोटे आ गोटे 1 इलेक्ट्रॉन लिखले.
कौन को नायोबियम रे
आज्ञा सर.
5s2 जगह 5s1 है
सर नहीं
D3
जो तले
40.
सर बन सर जो बॉक्स बनेला बेले
है
सर
तमे तो କରିପାରିବ ଚାରିକେ ପାଞ୍ଚଟା ଅନପେଡ୍ ଇଲେକ୍ଟ୍ରନ୍ କଣ ଦରକାର ଜାଣିପାରୁନ କି ଏଥିରେ ଚାରିଟା ହୁଣ୍ଡ 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 ଚାରିଟା 5s ରେ ଗୋଟେ ଏମିତି ଟୋଟାଲ ଅନପେଡ୍ ଇଲେକ୍ଟ୍ରନ୍ ପାଞ୍ଚଟା ହବ ହଁ କି ନାଇଁ
सर
ସେଠି
चारटा
ପାଞ୍ଚଟା
बदଳରେ ଆପଣ
କରୁଛନ୍ତି।
ପାଞ୍ଚଟା କରିଦେଇଛନ୍ତି.
କୋଉଠି ଲେଖିଛି ଚାରିଟା
सर बॉक्स रे बॉक्स
4 ତ କରିନି
44 ବକ୍ସ ଅଛି।
सर 4D ର
ଓ
ବॉक्स.
ଏଠି ବକ୍ସ କରିଛି ପୁରା ୟା ଓ ୟା ଏମିତି ମତେ ଦେଖେଇବ କାରଣ ଇଟ୍ସ ଏ ପବ୍ଲିକ ଭିଡିଓ it should have no mistake, or mistake free is a misnomer. Definitely, even in books written, authored by very distinguished persons, that book also carries some mistakes in the first print. Then that will be rectified later and later and later. So many after so many editions, you find the number of mistakes are reduced. Okay, but we must see that the mistake level is as less as possible. Yes, here there will be 4 and here there will be 1. Okay, but here there will be 6. And technetium, there is no anomaly. This is radioactive almost scarce element, radioactive, now used, prepared synthetically. That will be no anomaly. Anomaly, you can put a star mark or anything to show, to remember which are anomalous, which are having anomalous electronic configuration. Starts from niobium, then molybdenum as usual, yes. Technetium, no. Technetium doesn't suffer any anomaly. This is 5s2, 45. You can count the number of unpaired electrons, 5. But again, no anomaly. Then again, after technetium comes what? Technetium is falling on
Ruthenium.
manganese. Manganese, after manganese, iron, below iron, what?
Ruthenium.
Ruthenium, RUC. Ruthenium, RU. Ruthenium, then rhodium. Ruthenium is again anomalous star. Krypton configuration should have been 5s2, 46, between 5s1, 47. And you can count the number of unpaired electrons. It might be same in both the configurations, but the evidence from other studies, chemical studies and quantum mechanical studies, have proved that this is the real configuration in the ground state. And you can find out poly. So there are 3 unpaired electrons in the 4D and 1 unpaired electron in 5s. Right. Again, rhodium is 45. Again, it is anomalous. Krypton 4D8, 5s1. This 5s1 silsila is continuing. Only technetium doesn't suffer from any anomaly. And finally, the biggest anomaly will be found in palladium 46, is krypton configuration. No electron will be found. It should have been in this trend, it would have been 4d9, 5s1. No, it becomes 4d10, 5s0. And it is really, I will tell you just after a bit that it doesn't carry any unpaired electron. Its magnetic moment is 0. The magnetic dipole moment, spin magnetic dipole moment is 0, which is one of the evidences to prove that there will be no electron. Of course, had it been 5s2, 4d8, then it would have been also paramagnetic. Now I am giving you after a bit ke jaga chhado. So a thing is called paramagnetic species. Maybe ion, it may be anything. Atom, species containing unpaired electron. One or more UPE. The magnetic moment mu, spin magnetic moment is not equal to 0. It is non-zero. But on the contrary, some species are diamagnetic. About the properties of paramagnetic substances or species we'll know later. But I'm introducing the terms diamagnetic species. When we will explain the properties, then we'll be talking about ferromagnetic, ferrimagnetic, antiferromagnetic, so many other things we'll be doing. But now these two, paramagnetic species and diamagnetic species, no unpaired electron. The spin magnetic moment is 0. No unpaired electron species are called diamagnetic species. They are weakly repelled by an external magnetic field. But paramagnetic species like ferromagnetic species like iron, cobalt, nickel, they are attracted very strongly by a magnet. But paramagnetic species is their great child. So they are weakly attracted by the external magnet. Diamagnetic species are repelled. So those are the properties of paramagnetic substances. Diamagnetic will not write that here. So palladium is diamagnetic because no unpaired electron. And then comes silver. Silver, as usual, like copper, will be 5s1, 4d10. 4d10 is common for palladium and silver, but the difference is silver carries 5s1. One unpaired electron is there in silver. So silver gives only one state easily, Ag plus. But copper, being smaller in size, can give +1 and +2 both easily. Rather, +2 state is more stable in aqueous solution, because we will learn later, because of hydration energy, that when ion is formed and it is inside water, then it is hydrated, it is surrounded by a lot of water molecules, and attraction produces a lot of energy, that is called the hydration energy or hydration enthalpy. That makes copper 2 plus more stable than copper 1 plus. Although electronic configuration wise, D10 is a stable configuration, but the hydration energy from a +1 state is less than +2 state because size of copper 2 plus is much less than copper 1 plus, and therefore more the size, less is the hydration energy. Conversely, less the size, more the charge. The charge density is more, and hence more number of water molecules will try to surround it, and hence the hydration energy is more. That compensates for its unstable, less stable electronic configuration, 3D 9. Because if you take two electrons, 4s1 will go first, then 3D 10 becomes 3D 9. So that electronic configuration, the instability, that will be far more outweighed by the stability gain due to hydration enthalpy. That we will be knowing later. I'm just sounding you. Coming back to silver, then zinc is as usual nothing. This is krypton configuration. This is 30. Sorry. After zinc, cadmium. I'm sorry. Cadmium, this will be 48. As usual, there is nothing different. So put a star mark in silver. Silver suffers from, and also palladium. Rhodium, palladium, silver, all. But make a box in palladium to highlight that it is a very peculiar diamagnetic species having completely filled 4D. No electron is in the 4s. Sorry, 5s. This is 5s2, 4d10. Cadmium is diamagnetic, so there is nothing. Then you can continue at home. You will write the electronic configuration of all other in the fifth period in the P block: indium, tin, antimony, tellurium, iodine. This will be after exhausting 4d10. This is then 5p1, 5p2, 5p3, 5p4, 5p5, 5p6. There, for all these, the valence shell are 5s2 and 5p1, p2, whatever. The valence shell is not the n-1d. 4d is no longer the valence, it is completely filled. Electrons will go from 5s first, then, 5p first, then 5s, because p is more energetic than s. When you ionize, then you have to remove first from the 5p, then 5s. But in transition series, you first took from 5s and then 4d in the 4d series. In the 3d series, first from 4s, then 3d. Okay? Now we will go into the 5d. This is 3d series, this is the 4d series, and this is the 5d series. We'll go to the anomaly. Anomaly is lanthanum itself, which is 57. Now, before lanthanum, before sixth period comes xenon. We already know xenon configuration. We are entering into the sixth period, then 6s2. Then it should have been 4f1. But actually, the anomaly is this: 4f will not start filling, 5d1. This is the anomaly. Not 4f1, but 5d1. And quantum mechanical that has been.
Sir,
Hmm.
sir, lanthanum ର symbol ତ sir La.
La. Yeah, I'm so sorry. Ln is a general formula used for all lanthanides. I'm so sorry. And thank you, Mr. Mahanti, Master Mahanti, Master Swayam. Yes, La. Yes, that is anomaly. And there is no other anomaly, not in tungsten, not in anything. We come to platinum 78, there is one anomaly. Like, there was no such anomaly before platinum was palladium. Yes, palladium has the biggest anomaly of 5D, 4D10, 5s0. But here you will find the anomaly, one electron shift. The nickel was not having any anomaly in the 3D series. Palladium has double anomaly, and platinum will have anomaly. It will xenon configuration 6s2. Then instead of 6s, it should have been, because it is falling under nickel 28, 3D8, 4D8, 5D8. It should have been 5D8. You can just 54 plus 8 plus 2, 10. It should be. Uh, Oh, uh, this is 4F14. You have not writing. In Lanthanum, there was no 4D, it's 57. Now it is 78. So 6S2, then 4F14, then 5D10. So 54 plus 14 plus 8 plus 2. How much? Yes or no?
Yes, sir.
So
One.
here is an anomaly. It is wrong. I am just rubbing it off. It will be 6s1, 5d9 instead of 8. So, of course, the number of unpaired electrons being same. Had it been 5d8, 6s2, then number of unpaired electrons would have been 2, like nickel. But here also 2. There is 1 in 6s, 1 in 5d. But, other evidences, for example, exhibiting +1 state, which nickel doesn't, platinum does. So, and many other quantum mechanical calculation has proved that this is the real configuration, not 5d8 6s2. And then, as usual, the other one is uh, gold. Gold, like its younger brothers, siblings, copper and silver, it also has anomalous xenon configuration 6s1, 5d10. Of course, 4f14 will be there, then 6s1, 5d10. So we forget about these and we only take this 6, 1 unpaired electron in the ground state. Here, 2 unpaired electron. You have to open this. As long as it is not completely filled, you have to open and find how many unpaired electrons are there. And then calculate the spin magnetic dipole moment according to the n into n plus 2 square over bm, square root bm. So, of course, gold also shows two states, Au plus 1, that will knock out the 6s electron, and also Au 3 plus. So two more electrons have to be knocked out from 5d. It's not that copper plus 1 from 4s1 and then copper 2 plus another electron from 3d. Same is the case with palladium 2 plus. But palladium can, no, palladium doesn't show plus 1 because there is no electron in the 5s. All 4d10. So you have to knock out electron from 4d. So palladium also shows plus 2 state, usually. You can also knock out many more. 4 electrons you can also knock out. Gold shows 3 states, aurous and auric. Because the 5d electrons are farther away from nucleus, you can knock out 5d electrons. 2 more 5d electrons will make it plus 3. Why not Au2 plus? Why at a time, two electrons from the 5d, so that it doesn't show Au2 plus state? So that, again comes from the first ionization enthalpy, second and third, the difference between them compared to the hydrogen enthalpy. For knocking out electron, you need to invest ionization enthalpy. But after ionization, it is inside water, then you will get back. I mean, the ion will give you the hydrogen enthalpy. So you have to see the compare between these two. In some cases, the intermediate state is absolutely not, happening. For example, lanthanum doesn't show any variable valency. Lanthanum, La, as Soam pointed out, it shows only plus 3 state. So later on we will know that lanthanum is not regarded as a true transition metal. Transition block, it is a present in D block, in transition block, but it is not a true transition metal. Transition metal is defined as the metal whose ion, one of the ions, stable ions, will contain a partially filled D subcell. Partially filled D subcell, it should have at least 1 electron and 9 electron, not completely filled. So scandium immediately goes to plus 3 state. You cannot take out 4s1, 4s2 and then leave behind 3d1. No. The moment you remove the 2 electrons from 4s, the 3d electron is ready to jump. You cannot stop the 3d electron to jump and become scandium 3 plus. So there is always a comparison between the third ionization enthalpy, which knocks out the 3d electron, and what will be the size, reduced size and hydrogen enthalpy, so that you can compare, will that electron keep patience to remain and so plus 2 state? No, it is not. It is jumping. Once the 2 electrons jump, the third electron from 3d also jumps. So scandium shows only plus 3 state. That is why it is not having any ion, stable ion, which has an incomplete D subcell. So similarly, zinc is not a true transition metal. Zinc is only giving plus 2, no variable valency. 3d electrons are being so, stiff in the 3d series, being close to the nucleus, that 3d electron is not going to go. This ionization enthalpy is very, very high. The third ionization enthalpy is very, very high as compared to scandium. So it will not go, it will show only one state. So zinc is not regarded as a true transition metal. So also cadmium, so also mercury. These three falling into the group 12, they are not true transition metals. You may say that mercury is showing variable valency, mercurous and mercuric, but they are going from the 6s. 6s2 में से एक इलेक्ट्रॉन जाएगा तो हो जाएगा Hg+1. Both the electrons from 6s will make it +2. So it is no electron is going from 5d, although it is exhibiting variable valency. Because of the relativistic effect, I have not explained to you that mercury shows, but cadmium doesn't show variable valency. Zinc doesn't show variable valency, but mercury shows. But it is not a true transition metal. Now we shall be entering, and at home you will be writing the configuration. There is no anomaly in the normal block, the P block and S block, there is no anomaly. And so then you go for thallium. This will be 6p1, 6p2, 6p3, 6p4, 6p5, 6p6. Sixth period is complete with p6. Then the new period will begin with S7, S1, 7s2. Then anomalies again come here. Here nobody is no other phodium, dubnium, seaborgium, borium, hessium, ytnerium, dumstadium, rongenium, roentgenium, as I pronounced in my song, Roentgenium, copernicium, neonium, nihonium, plerobium, Moscow. These would be a speculative electronic configuration. You just add one in the respective following the Madelong's rule without looking to any anomaly. It's not been proved, any corroboration or anything. So what I am saying now comes the position of what are the anomalies in the lanthanide series and actinide series. Now, to save time, I will take you, because the file that I will be giving you is this one. This we have already done. Screening, which I've already told you. These things I have already told. Assignment is there, but I have given you more assignment. Oh yeah, I have given you to find out the electronic configuration of the ions. These are the simple ions where you remove 12 minus 2, 10. It will be having neon configuration. This will be 15 plus 3. 18 argon configuration. This will be helium configuration. This will be 8 like neon configuration. This will be again 8 13 minus 3 neon configuration. This will be 16 plus 2 sulfide ion is argon configuration. Just write down. And I have asked also to write the configuration of all these neutral atoms, but I have told you to write all, period wise and all that, with this short formula, Zenon configuration 6s1 for him, in this shortcut manner. Where,
Sir,
yeah,
sir, sir, Lanthanum କହିଲେ Genom 5D1 ଆଉ 6s2 sir, Lanthanum ର ତ ହେବ electronic configuration Xenon 5D1 6s2
yeah, 6s2 5d1, yes, the anomalous, yes.
ସେଟା F block ରେ କେମିତି ଗଲା?
A block ରେ ତାକୁ ଆମେ ରଖୁଛୁ କାହିଁକି ନା, because it is the mother of other lanthanide series elements. So we're keeping in the series at the bottom along with other lanthanide elements. So truly it would have been a D block element aguru bhi thila. And maybe 10 years before, IUPAC was not recommending to put, lanthanum and actinium along with the other 14 lanthanides and actinides elements respectively at the bottom, and emptying, making their positions vacant in the D block. So aguru se thila, but ebe semanku tole rakha jauchi to include them under this series. Lanthanide series contains lanthanum as the first element because of their similarities, because of the availability of other lanthanide elements in the mineral of lanthanum. Lanthanum minerals, they contain cerium and other things. So looking to their similarities, we have pulled down lanthanum and actinium down into the F series elements, although they do not carry electron in the F subshell, F orbitals. You will find the actinium also will suffer from the same anomaly. Let us write down actinium at least, then enter into other things. So coming to actinium, which is coming after radium, 88, this 86, this is 80, 88, this is 89, then comes thorium. You will find that the same anomaly that similar anomaly that we found for lanthanum will be valid. No 5F. 5F is not going to start. Interestingly, you will find in thorium also, you will not find the 5F orbitals are being filled. It will be D2. Again, you will ask me, Mr. Tripathi will ask, how it is in the F block. No, because we don't have any other choice. We don't have any other choice to put it in the D block. You have to. And they have similarities with protactinium, uranium, neptunium, plutonium. So they are there, but they do not carry electron in the F orbitals. Even thorium, I will tell you. So there is no vacancy in the D. And moreover, for lanthanum and actinium, you have to look to, although they do not carry F electrons, but their similarities with the other lanthanide and actinide elements respectively. Got it, Mr. Tripathi?
Yes, sir.
स्वयं बुझिल से बढ़िया
ଆଜ୍ଞା ସାର୍
बढ़िया क्वेश्चन पचारছে ଆଗରୁ ମୋଟେ ନଥିଲା ଆଗରୁ ଏଇଟା ପୁରୁଣା ନୂଆ ଆଚ୍ଛା ଏବେ ବି many scientists, teachers, scientists in US, they plead for the old method. They plead like you. but their number is very small. They challenge the IUPAC decision, the body which decides what to do and what not to do in chemistry. Similarly, IUPAP is a body in physics which decide what rules we will follow, globally. They are challenging, no? They do not carry F electrons, so let us put it in the D block. Show them in the D block. Why you are emptying in the D? That position is being vacant and you are keeping it down. So, they are shouting, the number is small, but others are following the IUPAC rule. Now, coming to the individual series. This we have already done. Transition metals we have already done. Yes, we have done everything. You will find if, yeah, these ions you have to write down. I have told to write the configuration of all the neutral atoms, but these are the ions. Or you can create any ion or find in a book any ion, transition metal ion or normal ion, plus or minus. You can add or subtract depending on whether it is positive ion, you subtract. If it is a negative ion, you add and then write down. Though the ions from normal elements are very easy, but transition elements, you have to see the electronic configuration of the neutral atom and then one by one from the highest energy orbital, then the lower. First 5s, then 4d, 6s, then 5d. Okay, you write down, and these answers, don't look to the answers. And in some cases, I asked you to find the spin magnetic moment for chromium plus 1. Chromium is 24 and it is 4s1. এটি ମୁଁ ভুল লিখেছি 4s1 এটি লিখিବା କଥା ମାନେ ବହୁତ ପୁରୁଣା ଏଇଟା ତାକୁ ମୁଁ କରିନି ଏଇଠି ମୁଁ ଚେଞ୍ଜ କରିଦେଉଛି ବିକଜ ଆମେ କାହିଁକି ଭୁଲ ଇଏ କରିବା ଆରେ ଲେଖୁନି କ'ଣ ଲେଖିବା କଥା ଏନିୱେ କ'ଣ ଆନୋଟେଟ୍ କରିହେବନି କରିହେବ ଦେଖିବା ଏବେ ଆରେ ନାଇଁ ରବରଟା କାମ କରୁନି ହଁ କାମ କଲା କାମ କଲା yes. So only one electron of chromium in the 4s1 that will become 4s0 and 3d5. So it will carry, instead of 6 unpaired electron, it will carry 5. So the spin magnetic moment is 5 into 5 plus 2 root over 35 root over bm. So I have already explained what is paramagnetic and diamagnetic. Just read out if any more information you get. These things. This you have already done. Now let us talk about the anomalous configuration in lanthanides. In lanthanides, these are the only three. Lanthanum you already know. Cerium will have an anomaly. The first element, after lanthanum, in previous periodic table, cerium was the first element, lanthanide element. Lanthanum was in the D block. Now lanthanum, then cerium. Well, that place is empty. So is 5d1, but remember that 5d1 should be stopped because one anomaly. The second anomaly you find, the 5d1 is continuing, but the 4f account starts. 4f का खाता अभी शुरू हुआ है सीरियम में. Again, in the middle, gadolinium, because of the half-filled stability, we have some, umbrella. Wherever there will be rain, in which direction we will show our umbrella to that direction. ବର୍ଷା ଯୁଆଡ଼େ ଛତା ସିଆଡ଼େ ଆମେ ଯୋଉଗୁଡ଼ାକ ହାଫ୍ ଫିଲ୍ଡରେ ପଡ଼ିଯାଉଛି ଚଲେଇ ଦେବା full filter podi jauchi explanation we will because we are a high school level student we cannot explain it quantum mechanically now so because of the uphill stability 85 6s 2 85 d2 hoba katha 85 d1 6s 2 ठीक अछि then एठी हम जदि कंटिन्यू करिया 4f टाको आगुर कोन थिला देखिबो 4f जोटा मेडेलॉन्स रूल अनुसार फॉलो करियो 5d9 नो एनोमली କିନ୍ତୁ ଏଇଠି 5D ଗୋଟେ ପଳେଇ ଆସିଲାଣି ଆଜ୍ ଲାଇକ୍ ଲାନ୍ଥାନମ୍ ସିରିୟମ୍ ଭଳିଆ 5D1। ତମେ ଏଗୁଡ଼ା ସବୁ ପୁରା ଲେଖିବ। ତମେ ଆଉଥରେ ଲେଖିବ ଅନ୍ୟ ଗୁଡ଼ାକ ଯୋଉଗୁଡ଼ାକ ମୁଁ ଛାଡ଼ି ଦେଇଛି ସେଗୁଡ଼ାକ ଲେଖିବ ନୋ ଆନୋମାଲି। ମୁଁ ଯୋଉଗୁଡ଼ାକ ଆନୋମାଲି ସେଗୁଡ଼ାକ ମୁଁ ପଏଣ୍ଟ ଆଉଟ୍ କରିଦେଇଛି। ବଟ୍ ଆକ୍ଟିନାଇଡ୍ସରେ ବହୁତ ଆନୋମାଲି। ଆକ୍ଟିନିୟମ୍ ତ ମୁଁ କହିଦେଲି 7:6D1 ଏଟାକୁ ସେପଟକୁ ନେବ। এটা ଆକ୍ଚୁଆଲି 6:2ଟା ସେପଟ ନେବା କଥା ମୁଁ ଛାଡ଼ କରିଦେଇଛି ତ ଆଉ 7:2ଟା ପଛରେ ରହିବ। 61 62 ଏଇ ଦୁଇଟାକ ଦେଖ ଥୋରିୟମ୍ 90ରେ 4F 5F ର ଖାତା ଖୋଲା ହେଇନି ସେ ଡିଟା କଣ୍ଟିନ୍ୟୁ କରୁଛି D1 D2 କଣ୍ଟିନ୍ୟୁ କରିବ 89 90 91 92 93 ପର୍ଯ୍ୟନ୍ତ କଣ୍ଟିନ୍ୟୁଅସଲି ଆନୋମାଲି ରହିବ କିନ୍ତୁ ଥୋରିୟମ୍ ପରେ ପ୍ରୋଟ୍ରାକ୍ଟୋନିୟମରେ 4F ଆରମ୍ଭ ହେଇଗଲାଣି। କିନ୍ତୁ ଆନୋମାଲି କ'ଣ ପାଇଁ 6D ମ୍ୟାଡେଲଙ୍ଗସ୍ ରୁଲ୍ ଆପ୍ଲାଏ ହଉନି କାହିଁକିନା 6D ଅଛି ବୋଲି। ସୋ ଲାଇକ୍ ଆକ୍ଟିନିୟମ୍ ଏଠି କିନ୍ତୁ 6D1 କିନ୍ତୁ 5 3 ହବା କଥା 5F3 ହବା କଥା 5F2 ସେଇ ସିଲସିଲାଟା ୟୁରେନିୟମରେ ବି ଅଛି। ୟୁରେନିୟମରେ ମଧ୍ୟ 6D1 କଣ୍ଟିନ୍ୟୁ କରୁଛି ଲାଇକ୍ ଆକ୍ଟିନିୟମ୍ ତାର ମଦର 5F3 ନେପଟୁନିୟମରେ ମଧ୍ୟ ସେଇ 6D1 ଅଛି 5F4 ତାପରେ କିଛି ଗ୍ୟାପ୍ ରହିଗଲା ପୁଣି 5 ହାଫ୍ ଫିଲ୍ଡ ଷ୍ଟାବିଲିଟି ଅଫ୍ 5F ସବସେଲ୍ ଭଳିଆ ଯେମିତି ହେଇଥିଲା ଲାନ୍ଥାନାଇଡ୍ରେ ଗ୍ୟାଡୋଲିନିୟମ୍ ତାର ତଳେ ଠିକ୍ ତା ତଳେ ଗ୍ୟାଡୋଲିନିୟମର ତଳେ ହେଉଛି କ୍ୟୁରିୟମ୍ ସେଇଟା ମଧ୍ୟ 6D1 and 5F7 anomaly and last interestingly ଆଗରୁ ତାକୁ ଆନୋମାଲିରେ ରହୁନଥିଲା ଯେମିତି ଲାନ୍ଥାନାଇଡ୍ ସିରିଜରେ ଯେମିତି ଲୁଟେସିୟମରେ ନାହିଁ ଲୁଟେସିୟମରେ ମେଡେଲଙ୍ଗସ୍ ରୁଲ୍ ଅନୁସାରେ ୟୁ ନୋ 4F14 6S2 4F14 ନାହିଁ 5D1 ନାହିଁ 5D1 ନାହିଁ କିନ୍ତୁ ଏଥିରେ ଲରେନ୍ସିୟମରେ ଆକ୍ଟିନାଇଡ୍ ସିରିଜର ଲାଷ୍ଟ ଏଲିମେଣ୍ଟରେ ଦେଖ ଆଗରୁ ନଥିଲା ଏବେ ସାଇଣ୍ଟିଷ୍ଟ have proved that D ରେ ଇଲେକ୍ଟ୍ରନ୍ ଆଉ ନାହିଁ ସିଧା ପଳଉଛି D କୁ ଛାଡ଼ିକିରି ଏପର୍ଯ୍ୟନ୍ତ 104ରେ 6D ଆରମ୍ଭ ହବ କିନ୍ତୁ ରଦରଫୋର୍ଡିୟମରେ ଆରମ୍ଭ ହବ କିନ୍ତୁ ଏଇଟା 5Dଟାକୁ ସରି 6Dଟାକୁ ଛାଡ଼ିକିରି ପୁରାପୁରି 7Pରେ ପଳଉଛି ଲରେନ୍ସିୟମରେ। They have studied the property lawrencium though its half life period is very less short lived କିନ୍ତୁ ଯେତିକି ସେମାନେ ତିଆରି କରୁଛନ୍ତି ଲରେନ୍ସିୟମକୁ ତାକୁ ପ୍ରପର୍ଟି କରିକିରି ସେମାନେ ପ୍ରୁଭ୍ କରିଛନ୍ତି ଯେ that the last element is in the 7p there is no electron in 6D so there is one anomaly so ଏତକ anomaly ଲେଖିବ ତା ଛଡ଼ା ଅନ୍ୟମାନେ ସବୁ ମେଡେଲଙ୍ଗସ୍ ରୁଲ୍ ଅନୁସାରେ ଫଲୋ କରିବେ। ମୁଁ ଏଠି ହାଇଲାଇଟ୍ କରିଦେଇଛି ପିରିୟଡ଼ିକ୍ ଟେବୁଲରେ କୋଉଟା anomalous ଏଟା ସୁପର anomaly 7p1 ଗ୍ୟାଡୋଲିନିୟମ୍ କ୍ୟୁରିୟମ୍ ଗୋଟେ ରହିବ Dରେ ଏବଂ Fରେ 7 ହେଇଯିବ ଏଗୁଡ଼ାକ ଦେଖ ପୁରା ପୁରା ଆକ୍ଟିନିୟମ୍ ଥୋରିୟମ୍ ଏଗୁଡ଼ା ଏଇଟା ସୁପର anomalous this will be 6D2 4 5F ର ଖାତା ଖୋଲିନି ଏଗୁଡ଼ାକ ସବୁ D1 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 ସବୁ D1 this is also D1 5F7 this is no 6D but 7p1 so I have asked you to find the ion supposing europium is this one europium is here it doesn't suffer from any anomaly 5D ରେ ନାହିଁ sorry 4F ଯଦି ଗଣିଦେବ 7 এটা 4F7 ये भी हाफ फील्ड बट 5D ରେ ନାହିଁ ଆ ଭଳିଆ ଗ୍ୟାଡୋଲିନିୟମ୍ ଭଳିଆ ତ ଏଠି 4Dରେ 5Dରେ ନାହିଁ ୟୁରେନିୟମ୍ 2+ ହେଲା ବେଳକୁ ମୁଁ ଲେଖିଛି ଭୁଲ 6S2 ଏଠିକି ଆସିବା କଥା so 4F ରହିବ 6S ଯେହେତୁ ହାଇଏଷ୍ଟ ଏନର୍ଜି ବିକଜ ଅଫ୍ ସ୍କ୍ରିନିଂ ଅଫ୍ 4F ଇଲେକ୍ଟ୍ରନ୍ସ so 6S ରୁ ହିଁ ଯିବ 4F ରୁ ଯିବନି ମୁଁ ଲେଖିଛି ଭୁଲ କହିଛି ଠିକ କିନ୍ତୁ ଲେଖୁଛି ଭୁଲ ଏଠି ମୁଁ ଚେଞ୍ଜ କରିଦେବି କେତେବେଳେ ସମୟ ପାଇଲେ ତମେ ଲେଖିଲା ବେଳକୁ ଆଗ S ଲେଖିବ ତାପରେ D କିମ୍ବା F ଆଗ NS ଦେନ୍ ତା ଜଷ୍ଟ ପୂର୍ବଟା ହେଉଛି N-1D ତାରୁ ଆହୁରି କମ ଏନର୍ଜି ହେଉଛି N-2F ତେଣୁ ଗୋଟେ ଲିଷ୍ଟ କରିଦେଇଛି ଯେଉଁମାନେ ମେଡେଲଙ୍ଗସ୍ ଅର୍ଡରକୁ ଫଲୋ କରୁଛନ୍ତି 20ଟା Lanthanides actinoids which follow normal Madelung's rule 20ଟା ବାକି ଯୋଉଟା ଲିଷ୍ଟ କରିଛି ଏଗୁଡ଼ାକ you will find these are anomalous isotopes କାହା କହନ୍ତି isobars କାହା କହନ୍ତି I think we will close today's session and then after this you can read out and solve assignment ସରିଗଲା actually but let me quickly tell you isotopes already ଜାଣିଛ ପିଲା ବେଳୁ same atomic number but different mass number they have different number of neutrons. Isobars hala mass number same rahila, different atomic numbers. So that they have different number of protons, but the mass number is same. So what is the similarity? The only mass number is same. Number of neutrons also they are different. Number of neutrons different, number of protons different, but the mass number is same. Example the argon 40, potassium 40, which is a radioactive isotope, and calcium 40. Isotones same number of neutrons. Same difference same होतो. Potassium 39 isotope, calcium 40 isotope. They have same number of 20 neutrons. Isodiapers are different elements with same neutron excess. Neutron excess, proton ठारू neutron केते अधिका अछि. न्यूट्रन नंबर याकू फेडी देले जतिक हबो माइनस प्रोटॉन नंबर 54 टा न्यूट्रन एक्सेस एथरे भी अछि थोरियम 234 आइसोटोप रे यूरेनियम 238 आइसोटोप रे मध्य न्यूट्रन एक्सेस 54 टा अछि तेणु दोज व्हिच हैव सेम नंबर ऑफ न्यूट्रन एक्सेस आर कॉल्ड आइसोडायफर्स. So this is the end of today's class. Coming class re hame shapes of orbitals, nodes and Schrodinger's equation ro jo functions जो wave function of different orbitals ताकू आमे देखिबा जानिबा एवं से अनुसार ग्राफ ड्रा करिबा between psi versus radial distance, psi square versus radial distance, and some probability density d versus radial distance. Stop pore ame quickly sariba photoelectric effect, then Moseley's experiment on atomic number, and some other things we shall be doing, and maybe within 2-3 classes we'll be finishing. Bye bye. Lot of home tasks you'll find. Lot of home tasks I have given in the slides. I mean in the PowerPoint file that I will send you. And also I have also told you that समस्त हमर बाहर करो. शायद जेनन ता पूर्व नोबल गैस अनुसार तो करियो बहुत इजी है. Bye bye.
Thank you, sir.
Thank you, sir.